Hello everyone and welcome back to chapter 22. We have part 4 of the chapter, and in this video we're going to do one more derivation for the electric fields, but then we're going to take this derivation and we're going to apply it in a way that we wouldn't really be able to apply many of the other electric field situations that we've had. And that's because we're going to scale things back down to a two-particle system. And so far, we've been able to use the point charge expression to tell us what the magnitude of the electric field for a single particle would be. And then in the last video, we said that we were going to start rewriting the value of k in its expanded form, 1 over 4 pi epsilon naught, because we're going to need to get into the habit of seeing those terms written out when we get to chapter 23. So for this example and for all other examples that we're going to see, I am going to start writing out the value of k as 1 over 4 pi epsilon naught, but feel free to continue taking that entire construct and using the value for k that we've been using this whole time. No reason we can't keep doing that. So for this two-particle system that I talk about, we've also seen examples where we can add together the electric fields that are being produced by multiple charges. And we've actually seen a couple of examples where we had multiple charges, not just two, but a couple of the examples we saw had 4 particles in a system. And if we can add up 4 particles, then adding up the contributions of 2 particles shouldn't be all that demanding of us. So this particular 2-particle system is what we're going to call an electric dipole. And this is a special construct of charges where we have one positive and one negative charge. Each of these is the same magnitude of charge. It's just that one of them is positive and the other is negative. And then they are connected together, or what we could say is that they're separated by a fixed distance that we will call d. And so they're like 2 charges that are stuck on the end of a stick. And so these charges would like to come together because there would be an attractive force between them, but because they're stuck to the end of that stick, they have to remain physically where they are. And so what we want to do is we want to figure out what is the electric field that this pairing of charges is producing up at point P. And if we considered allowing these 2 charges to actually move, then the charges would come together, they would form a null charge, and then the math would basically collapse and we would not have a field up at point P. But that's the reason why we want that little stick in the middle there to keep them separated. And the reason that this is so important is because there are a lot of electric dipoles in chemistry. When you start putting together different atoms and you start constructing molecules, those atoms do not necessarily space themselves out in a symmetric construct. A really good example would be a water molecule. which is made up of 2 hydrogens and an oxygen. And so I'm going to put an oxygen ion right here. Oxygen will form a -2 ion, and then the hydrogens will bond on one side of the oxygen. And because of that, what happens is that one side of the molecule becomes more positively charged, and the other half of the molecule becomes more negatively charged. And because of the physical structure of that water molecule, there is a fixed distance between the two ends of this polar charged molecule that can be measured. And so a water molecule constitutes as a dipole. It has an electric dipole, and so because these two charged ends are separate from one another, these two charged ends can then produce electric fields in the surrounding area that will affect other nearby molecules, like maybe another water molecule. And so this is why water molecules have a tendency to stack, and that's because the positive ends of one molecule are attracted to the negative end of another water molecule, and so on and so forth. There are other molecules and chemical compounds out there that are polar, but there are also plenty of molecular compounds out there that are not polar. There are compounds out there that can actually spread themselves out in a more uniform, symmetric fashion where you don't get this polarity effect. But because we do have so many molecules out there that do behave as dipoles, that behavior can affect how the chemistry of the system plays out. And so we want to know, since things like electric forces are far more influential at the microscopic scale than things like gravity forces, then we might want to know what kind of electric field this dipole construct produces. And so now that we've got that explanation out of the way, we can actually start the setup for the math that we need to do. Now, one good thing about this, since we only have 2 charges, we don't have to set up any complex calculus expressions to add up all the influences. We just have to add up these 2 particles. Where things are going to become more difficult is how our author wants us to describe the final expression. The first thing that we're going to do, we're going to define a characteristic of this dipole, which is what we call the electric dipole moment. And we call this P, and it is a vector. Now in Physics 1 we used P for momentum, but momentum incorporates mass. We're not really using mass anymore in this class, so now P stands for the dipole moment. And the definition of the dipole moment is going to be the magnitude of the charge. So each of these charges has a magnitude of Q, and the displacement that exists between the 2 charges. Now, the dipole moment P is a vector, and so that means that one of the 2 terms on the other side is going to have to carry the the vector hat. Charge is a scalar, so it can't be charged, and that means that the displacement between the two, if we remember back in physics 1, displacement is a vector, and so we can designate that displacement as a vector, but every vector has to have a direction associated with it, and so the direction of D will point towards the positive charge in the dipole construct. And so that means that the dipole moment, P, will point in the same direction as D. Now I'm already using P to designate the point out in space where I want to measure things. So let's get rid of that, and we can just put E up here since we want to know what the electric field magnitude is up at that point. And whoops. And I don't really need the dipole moment vector in my diagram just yet. We're going to come back to this later on as we're trying to clean up our final expression after we've put everything together, and we're gonna summarize what we have, and we will see the pairing of Q and D show up in our expression, and so we're going to replace that with P, but that's not going to happen until the very end of our discussion here. So our author wants us to incorporate this electric dipole moment into our final expression, but the author also wants us to measure everything with respect to the midpoint of this dipole, which is kind of strange, because if I'm going to figure out what the electric field is that is produced by the positive charge up at that point, then I would need to know how far away that positive charge is. So I would call that R of the positive charge, and when I say R, I mean the R value that's going to go into our electric field expression. And I would also need to know how far is the negative charge from the point in space where I'm trying to measure things. But the author says, well, you need to measure from the midpoint of the dipole. And the author has kind of gotten into the habit of using Z to measure that distance from our charge collection. But this still doesn't explain why the author wants us to measure from the midpoint of the dipole. So to answer that question, if we go back to, say, the water molecule with the hydrogens and the oxygens, if I wanted to measure the electric field that this water molecule was producing, well, the distances between the positive end of the water molecule and the negative end of the water molecule, they only differ by the value of D. And in comparison, the value of D compared to the separation distance that we have to the point out in space where we're trying to measure things, Z is probably much larger than D. And so it probably wouldn't make a whole lot of sense for us to try to measure things from one end of a very, very small molecule to another. We could just average things out and measure from the midpoint. And so that's the goal of our author. The author wants us to, oops, I wanted to use my eraser function there. The author wants us to measure from a midpoint in the hopes that maybe it'll make the math a bit simpler, but let's not get our hopes up there. All right, so here we go. We need to find the magnitude of electric field up at this point, and we're gonna start with what we know. We need to find the net contribution of the electric fields that are being produced by the positive charge and the negative charge. Now, don't let those plus and minus signs mislead you. We're not just going to combine them and set them equal to 0, because they are not the same distance from the point that we want to measure at. So next I will incorporate the point charge expression for each charge. For the positive charge, we have K. We have positive Q over the positive R value, so the distance that the positive charge is from the point where we're measuring. And then we add to that the field that is being generated by the negative charge. So once again we have K, but now we have negative Q over R negative squared. And that negative Q, that negative sign, is going to carry out to the front of that term. And so now we can work with magnitudes here. Both of those terms are using the same magnitude of charge, but one was positive, one was negative. Again, don't go through and cancel everything out, because the R plus and the R minus terms are different. So we can't just cancel everything out right now. But here's where we can actually combine those two denominators. Right now we've got the combination of two fractions in front of us. They both have a common value of K. I can also factor out the Q. But what's left is the combination of 1 over R positive squared minus 1 over R negative squared, and we need to combine those two. So the way we're going to do that is we'll look back at our diagram that has all of these different distance measures, and we need to figure out how we're going to write R positive and R negative in terms of the things that the author wants, like D and Z. And we can see how that's going to happen now. If we travel the distance of R positive, we've almost traveled the full length of Z, except we would need to go a little bit further, and the value of that extra displacement there, well, that would just be half the value of D. And so we could say that R positive is equal to Z plus half the value of D. Then we need the value of r negative. So if we come all the way down r negative, well, we've not only gone the full length of z, but we've also gone an additional distance of half of d. And in one moment here, I've made a mistake that I just caught. When it comes to r positive, we have to come down the full length of z, and then we have to backtrack half of d2. So apologies there. This needs to be a minus sign. And then this is the plus sign. All right. Those are the substitutions that we're going to make into our equation thus far. So E net is now equal to Q over 4 pi epsilon naught. We have 1 over r positive squared is now z minus d over 2 squared minus 1 over r negative squared, which is now z plus d over 2 squared. And the next step, now that we have things written in the form that our author wants, hence using d and z, we need to figure out how we're going to combine these two fractions. And back in elementary school, we learned that the only way that we can combine fractions is if we have a common denominator. But I don't know what the values of z and d are going to be. Not only that, there are plenty of different kinds of dipoles out there where these values can shift, so I need a more general approach. And so when all else fails, we can just multiply the two denominators together, and that will ensure that we have a common denominator. But if we're going to do that, what we do to the bottom, we have to do to the top. And so, long story short, we're going to do a cross multiplication between our values. And so what we're going to see is a z plus d over 2 squared over z minus d over 2 squared. Actually, I'm just gonna jump to the end result of combining these two. So we're going to have z plus d over 2 squared minus z minus d over 2 squared all over the product of the two, which is now the common denominator. And you're probably thinking at this point, this is starting to turn into an algebraic nightmare, and to an extent I would agree. But now this is technically the answer. This is the net field expression. We just need to take a little bit of time to see if we can break this down into something that's more user-friendly. And where I'm going to start is up in the numerator, because we have two binomials that need to be subtracted from each other. And so let's take those binomials and let's see what we get if we expand them. So this first one would be z squared plus 2z d over 2 plus d squared over 4, and these 2's will cancel. So we just have ZD in the middle. And then for the second binomial, we would just get the opposite in the middle term. We would still have z squared, but then we're going to have a minus ZD plus d squared over 4. And these two terms have to be subtracted from each other. So let's go ahead and subtract the bottom from the top. When that happens, we have z squared minus z squared. Those are gone. We have d squared over 4 minus d squared over 4. That's gone. We have zd minus a negative zd, so that's a 2zd. So the whole top has collapsed down to that. But then we still have the bottom. And at this point, I don't really want to carry through the math on the bottom right now, because in the interests of saving us some time, there is another probably 2 to 3 pages of algebraic manipulation that comes with this, which might make for a good individual exercise just to sort of strengthen your algebra skills. But for a lecture video like this, I don't think that we really need to spend a whole lot more time on this. So if you don't mind, I would like to jump to the end result. So this is where basically you've got some hand-wavy math, or I'll just say physics magics, just magic. And so we're going to get to an end result which says that the magnitude of our net electric field, so this whole way down we're talking about the magnitudes of net. So what this is going to eventually boil down to is that the net field will be 1 over 2 pi epsilon naught. And you might say, well, what happened to the 4? Well, it happened in the magic step, along with qd over z cubed. So again, there's a lot of stuff that breaks down and simplifies in all these math steps. And so if you want to, go ahead and give that a try. See if you can get from here to here. That's actually a very common thing to see in more advanced coursework. It's always something I hated to see. We'd be reading through a textbook and we'd get to this point, and then it would say something like, it is left to the student to show that you get from here to here. And then that would be a homework assignment, basically. But now we can combine what our author wanted earlier, which is the definition of the dipole moment QD, with the final expression right here. So now the net electric field, or as we can just call it now, the electric field that is being produced by the dipole directly above the dipole itself. This has to be directly above the central axes of the dipole. This isn't going to work anywhere else in space, except maybe if you were below it. So as long as you're on this central axis of the dipole. Oops, I wanted that to be red, but we'll try blue. As long as you're on the central axis of that dipole, you can use this expression. Anywhere else, you would have to go back into your derivation process and start introducing some trig functions, which you know, the algebra for this has already been extreme enough. We're just going to go ahead and cut our losses here with the one-dimensional case. So our electric dipole is 1 over 2 pi epsilon naught p over z cubed. And since the dipole moment is a vector, we can then say that the resulting electric field is also going to point in the direction of that dipole moment. Okay. Now that we have the electric field that the dipole is producing, we want to take that dipole and we want to see how it would behave if we were to insert it into an external electric field. So what I'm going to do here is I'm going to draw some arrows here, and these will indicate the direction of an external electric field. So these field lines are being generated by some source of charge which is currently off to the side of the page. We can't see it. All we know is that we have these electric field lines that are entering the region. Now, if we were to drop a charged particle into this system, well, what would happen? So at the beginning of this chapter, we learned that we could rewrite the force expression as a combination of field and charge. And the direction of force should be in the same direction of the field, assuming that we're using a positive charge. And so we would see an electric force start to push that positive charge to the right. Conversely, if we had a negative charge, then, whoops, wrong symbol there. If we had a negative charge that we placed into the electric field, that sign would then flip the direction of the vector, and we would see an electric field producing a force in the opposite direction. Now, one way that I kind of justify this picture to myself is I think back to how these electric field lines would be formed. And we know from our discussions in this chapter that electric field lines will extend outward from positive charges. And so there could very likely be a very large sheet of positive charge over here somewhere producing those electric field lines. And we know that positive charges repel, and so that's why we have our force pointing to the right. We also know that opposite charges are going to attract, and that's why we have that force pointing to the left. Well, now we're not going to have just the individual particles. We are going to insert a dipole into this system. So the dipole has the stick that is essentially holding the two charges together. But that's not going to change the fact that once we place this dipole into that external electric field, that there won't be forces involved. Now, for this discussion, please note that the electric field that we're talking about is an electric field that is coming from some outside source. It is not coming from the dipole itself. Up here we were talking about the electric field that a dipole could produce, but now we're talking about what's going to happen to this dipole if it's affected by an outside electric field. Well, once again, we're going to see those forces acting on the charged particles in the respective directions. But because the particles are connected together, because they have to maintain that separation distance of d, well, what's going to happen is that the dipole is going to start rotating. We have these forces that are tugging on either end of the dipole, and we're going to start seeing the dipole start to rotate in this clockwise direction. Until at some later time, doesn't want to change colors for me. There we go. So until at some later time, our dipole has rotated 90 degrees, but the orientation of the forces has not changed. We're still going to see a force pulling to the right on the positive charge. We're still going to see a force pulling to the left on the negative charge. And when we get to this orientation, trying to pull left and right, this is not going to continue providing any rotation for the dipole. And so the whole idea behind this rotating dipole, if we go back to the last chapter that was covered in Physics 1, everything there had to do with rotational motion. And when we apply a force to any object that is going to start rotating, what happens is that we get something called torque. And back in Physics 1, torque was defined as the combination of force applied at a given radial position. And we combine those two using a cross product. So the torque becomes a vector itself, and that vector is found by carrying out the cross product. And so the way that we evaluated the cross product, it was similar to the dot product, but we have to use a different trig function. In the case of the cross product, we use a sine. And so there were three considerations for how an object is going to rotate. We had to know how much force was applied, we had to know where that force was applied, and we had to know how that force was applied. And when I say how, I mean how is the force applied with respect to the radial vector. And the radial vector is very easy to find. We just start at the pivot point, which is right in the middle of the dipole, right here. And we just draw a line that goes out to the point where our force has been applied. And that's the radial vector. What we can see here is that the angle between the radial vector and the force vector is 90 degrees. And if we plug in 90 degrees for theta, sine of 90 is 1. All we get for the torque is the multiplication of R and F, which in our case R, let's see, how far is R? What color should we use here? I'll try purple, see if that shows up any better. The distance for R, where we have to apply the force, that's just half of the separation distance between the two charges. That's d over 2. So I can replace R with d over 2. But then that force, well, we've been using that expression since the beginning of the chapter, QE. We can sneak that in there. And so now we have an expression that tells us what the torque is going to be, no longer in terms of the physics 1 material, but now in terms of the physics 2 material. Now I still have the torque over here written as a vector, so I'll write that as magnitude, but if I want to revert back to vector notation, I would need to figure out a way of writing this as a cross product representation. Of everything that I have in this expression, Q and the 2 are scalar quantities, but D is the separation distance between the two charges. And if we remember, P has to point in the same direction as D, so we've got D. And E is a vector as well. QD equals the dipole moment. And if we look at the angle relationship between P and E, P is pointing straight up, E is pointing to the right. That's the same angle relationship of 90 degrees as what we had for the radial vector and the force vector. And so we can get away with using the same sine theta relationship. And well, now we have a torque expression that says half of the cross product between P and E would provide us the same torque expression. Now, keep in mind that everything that we've discussed so far has only pertained to that positive charge on the top. Well, what's happening with this negative charge down here? That negative charge is also at a radial distance of d over 2. That force acting on the negative charge is also at a 90-degree angle. Everything about that negative charge on the bottom is going to produce the same amount of torque as what the top force provided. And like the top force, the bottom force is going to induce rotation in the same clockwise direction. So we're getting twice as much torque by combining the two. As such, we now have a net torque acting on our dipole moment that is equal to P cross E. So we had twice as much as what we had up here, so now we lose the 2. Alright, so now we know how much torque we're getting out of this rotating dipole. If we take that idea of P cross E and we go back to our sine theta notation, well, what's happening up here now? Once our dipole reaches this particular orientation, if we look at the direction that the forces are pointing versus the direction that our radial vector is pointing. So again, to find your radial vector, you just start at your pivot point and you draw a line out to where your force has been applied. But now the angle between these two is 0 degrees. If I plug that into my sine theta relationship, sine of 0 is 0. How does that work with the P cross E? Well, I still have my electric field vectors pointing to the right, and our dipole moment always points in the direction of the positive charge of our dipole, and so those two are also running parallel and have a 0 degree relationship. So once we get to this orientation, there's no more torque. There's no more potential for the system to want to continue rotating. And so that means that the torque acting on this dipole is constantly changing with respect to that angle theta. So what can we do with that torque expression? I mean, it's nice. I guess it's nice to know, but what are we going to use it for? Well, we're taking a dipole. I'm going to draw a fresh picture here. We're taking a dipole, which, as much as we're trying to avoid it, this dipole has some mass, and we're applying a force as a result of having this electric field act on the dipole, and this force is causing the dipole to rotate. But that means that it's moving. And we know from physics 1 that if we apply a force and we get something to move, in other words, if we get something to displace, then work is done. And work is defined as a change in energy. Oops, energy. Try that again. Energy. There we go. Well, what energy can we have that's changing? And if we're going to change an energy, how do we conserve the energy in the system? So this brings us back to another Physics 1 concept, conservation of energy, which says that whatever kinetic and potential energy you start with in the system has to equal the combination of kinetic and potential at any other point in the system. So right here at our initial starting point, there's some combination of kinetic and potential energy, but then the system causes our dipole to rotate, in a sense displacing, and so there has to be some combination of kinetic and potential energy later on. Now, as our force is applied to our dipole, as we're displacing, one of the things that we really focused on in Physics 1 is that all the work that's done changes the kinetic energy of the object. So these forces that we're applying to our dipole, they're taking the dipole from an initial rest position, so we would have 0 kinetic energy to start with, and then we start moving, and now we have a kinetic energy that would not equal 0. So we're increasing our kinetic energy by rotating this dipole, but we can't just make energy out of nothing. It has to come from somewhere. And so any change in the kinetic energy for the system will have to be offset by any change in potential energy for the system. And this had to be in an equal and opposite amount. So if our kinetic energy goes up, our potential energy has to go down, such that the total energy in the system remains constant. Well, we can actually find some of those energy values by using the torque expression that we came up with in the discussion above. Also, in the last chapter of Physics 1, we saw that for a rotating system, the work that was done, well, we can't use the linear definition of work, where we have a force carrying us in a displacement, because we're not moving in a straight line. We don't have a linear displacement, and we don't have a linear application of that force. So instead, in that particular chapter, we had a way of rewriting term for term these expressions to get an angular equivalent of work, which says that we need to know how much torque is applied over a given angular displacement. Well, we know that now. We know that there is torque in the amount of P cross E, which is being applied over a given angular displacement. In this case, we're allowing our dipole to displace through 90 degrees, but that angular displacement can really be anything that we want. We can displace 90 degrees, 45 degrees, 30 degrees. We can even go past 90 degrees if we want. And so if we take this idea that work is the product of torque and angular displacement, well, we have our torque expression. It's P cross E, and then I have to combine that with the angular displacement. Well, this right here, this just expands out to PE sine theta, but then we've got this delta theta thing over here, and you're like, well, what am I supposed to do with that? And if this is a delta theta, if I can start at one theta value and end at another theta value, like 0 and 90 degrees, well, what am I supposed to put in for sine theta? Well, this is actually an instantaneous theta value. This could be any theta value in between that range, and that's not going to work for us if we're trying to evaluate how much work that we've done. So instead, what we need to do is we need to take that instantaneous theta value and apply it to an instantaneous change in theta. And that means applying an integration. To make sure that we have a definite integral, we need to incorporate some limits, and like I said, we can really go from any theta value that we want during this rotation. So we'll just plug in generic initial and final theta values. P and E at this point are now constants. They can come out front. but we have to integrate sine of theta. So integral sine theta is negative cosine. So we get negative PE cosine theta evaluated at the limits. So again, these can be any start and stop points that you want, including these. But I'm gonna leave this in general form right now. And what we can do at this point is we can go back up and we can actually choose which of the two energies we want to compare this to. If we want to say the change in kinetic energy, well, we've got exactly what we need there. Theta not theta final. Or if we want the change in the potential energy, remember that change in potential energy was equal to minus the change in kinetic energy, so we're going to lose that minus sign. But what do you get when you have two vector quantities paired with a cosine that produce scalar quantities? Well, this is a dot product. And so the change in our potential energy is really just the dot product of the two vectors that we've been using at this point. If I want to switch that over to the kinetic energy, then I slap a minus sign in front of it. But now we can see that to find the torque in a system that involves a dipole moment, we would take the cross product of the two vectors, whereas if we want to look at how the energy in the system is changing, all we have to do is switch over to the dot product in the system. And you still might be asking yourself, well, why is this kind of stuff important? Why do we need to know how a dipole rotates in a given electric field? Well, back to the water molecule. Our water molecule was a dipole, and I'm just going to draw our water molecule as a dipole now. And let's say you take something that has water molecules in it, like TV dinner that happens to be frozen. Right now those water molecules are in a solid state. But you take something like I don't know, a frozen meatloaf dinner or something, and so that slab of meatloaf has billions and billions of water molecules in it. And what you're going to do is you're going to stick this into the microwave, which introduces alternating electric fields. And what's going to happen is, as these electric fields pass through the meatloaf, they're going to cause a torque to occur, which means that all of these water molecules are going to rotate. But then we don't want all these water molecules to just rotate to a horizontal orientation and stay there. And so that's why we alternate the electric field that passes through the system, and this forces the water molecules to alternate back and forth. So they're going to flip back and forth, back and forth, back and forth. And as they do that, they're constantly changing their kinetic and potential energies, but it's slightly more complex because we now have to have another entry into our conservation of energy equation, which is any thermal energy that might happen to be generated by any friction that is caused by having all of these water molecules reorienting themselves back and forth. So what happens is that we're we're introducing energy to the system by the alternating electric fields, but then those energies end up transferred to the dipoles, which then start oscillating back and forth, causing friction, causing your food to heat up until it gets to the proper temperature that you can eat it. And so your microwave quite literally works on the idea that we have the proper frequency of electromagnetic radiation that alternates the water molecules at an optimum frequency so that we can heat up the food. So what do you think would happen if you put something in the microwave that did not have water molecules in it? Well, in that case, there are certain things that will react, but they're not going to react in the designed purpose of the microwave. So I shouldn't have to say this, but don't try this at home. Don't throw anything other than food items into your microwave. But when I was a kid, I tried melting a candle in the microwave because I had to have liquid wax for a project. I figured it would be quicker if I just put it in the microwave, and after a minute, nothing. 2 minutes, nothing. I kept microwaving it, and just nothing was happening. And that's because there was no water in the wax. All I had were these hydrocarbon compounds, which were not polar, and they weren't going to oscillate with the changing electric field, and so the wax would not melt. So very, very interesting how we can take this physics and apply it to the real world and actually get some things done, like cook our dinner. So I think that's going to bring us to the end of the chapter 22 material. Go ahead and give the homework a try. The homework is basically going to be taking the equations that we've been producing, applying them to some different situations. Go ahead and contact me if you're having any troubles with any of those. And until then, I'll see you at the next video.